In this video, we're going to be talking about different types of distributions, but focusing on one very special distribution called the normal curve. Let's begin. So in our notes, we begin by noticing that there are several different types of distributions where our data could be living. So we could have data in which you have basically these histograms where your frequencies are your vertical and then each class is your midpoint, represented by each midpoint of the bar. So we notice in this case that most of those bars are heavily to the right. We would say that's skewed to the right, whereas in this case, most of the bars are skewed to the left. So we would say that's skewed to the left distribution. Other types of special distributions that we notice are rectangular distributions in which every single class has the same frequency. We would say that the heights are all the same, making a basic rectangle. So that would be very easy to calculate the area that is represented by those, just length times width. On the other hand, when we have two modal classes, I should say, we would say we have a bimodal distribution. So we have two classes which are tied as the most popular classes. Finally, the ones in your notes that you need to fill in are called J-shaped distributions. J-shaped distributions. So a J-shaped distribution is simply a distribution which is constantly increasing or decreasing. So we notice that the classes are increasing from left to right in this J-shaped distribution on the left, and on the right here we have another J-shaped distribution where we're constantly decreasing. So that's what we call J-shaped, because you can make a letter J if you were to draw on top of this one here. Now the ideal distribution that we're going to spend most of our time on is the normal distribution. The normal distribution is the name we give to a bell-shaped distribution. So if we have a situation like this, we would say that a normal distribution will always be bell-shaped. Will always be bell-shaped, and that the graph has nice symmetry. In fact, it's symmetric about the middle here, and right in the middle, that's what we call the mean. Okay, so the average will be in the middle. In fact, not only will the average be in the middle, but the middle score, the median, the mode, and the mid-range will all be the same at that location. And that will be in the center of that graph. So it's very nice because once you know what happens on one side, you know what happens on the other. It's highly symmetric. And we'll be talking more about some tricks that we can use once we know that our data is normally distributed, bell-shaped. So let's take a look at one example where we talk about the number of standard deviations, which we could be from the mean. So let's take a look. Example 1 says, IQ scores are known to be normally distributed with an average IQ score or a mean of 100 and a standard deviation of 15. What we mean by standard deviation is, on average, how far scores lie from the mean. Okay, so that's what we talk about for standard deviation. We've calculated it in the past. So 15 is our average deviation from the mean, so it's our standard deviation for IQ scores. How many standard deviations from the mean would these IQ scores be? So suppose we're talking about the IQ score of 85. In statistics, we'd call this letter X. What we would notice here is on our bell-shaped graph, if it's truly a normal distribution, we could put our mean right in the center of the graph. So this would be like X bar if it's a sample mean. Okay, so this would be our mean, and the mean is 100 in this example. All right, so what we're noticing here is that because the standard deviation is 15, if I went 15 units to the right, I'd be at 115 for my IQ score. That would be one standard deviation above. But if I went 15 units to my left, what's 100 minus 15? That's right, 85. So if I went one standard deviation to the right, I'm 115 IQ score, and one standard deviation left of the mean is 85 for IQ scores. So the question was, how many standard deviations would 85 be, the IQ score of 85 be? Well, it looks like it's one standard deviation below the mean. So we would say it's just one standard deviation below our mean. Now that tells us something. We're going to talk about something called the empirical rule in a few moments. And by knowing that you're exactly one standard deviation below the mean, that's going to be telling you that there's a certain probability that that's likely to happen. So we're going to be able to figure out that probability known as a percentage very soon. All right, what about 130? Part B says, what happens if you have an IQ score of 130? How many standard deviations away from the mean would that have been? Well, once again, the mean for a bell curve is in the middle. So we'd say if X bar, our sample mean is 100, then we could go up one standard deviation and be at 115. Two standard deviations, we'd be at 130. So we are 2 standard deviations above the mean. 2 standard deviations above our mean for an IQ score of 130. All right, so now what does that tell us? What does that mean? No pun intended. Well, the empirical rule is going to give us an idea of once we know that we're 1, 2, or 3 standard deviations away from the mean for a certain score, we'll know what likelihood that is to happen or what percentage of the population lives there. So let's take a look at bell-shaped curves and something called the empirical rule. So the empirical rule only applies for bell-shaped curves, normal distributions. The first thing we notice is that the mean would be in the middle, right? That's our x bar. And it cuts the graph in half. So 50% of the population should be below and 50% should be above. For example, if your professor gave a test and the average score on the test was a 70%, if it was truly a bell-shaped graph, half the class would have scored below a 70 and half the class would have scored above a 70, 50% on each side. That's what we mean by symmetrical here. Now what we're going to notice is for any true bell-shaped curve, any true normal distribution, this empirical rule will hold, okay? So you are going to need to memorize it and be able to use it like we will in our examples today. The first one I want to point out to you is what if you went 1 standard deviation to the left or to the right of the mean? For IQ, that was at, I believe, 115 or 85, right? That would be within 1 standard deviation of the mean. It turns out that 68% of the population will always live within 1 standard deviation of the mean. So if this was IQ, 68% of the population would have an IQ score between 85 and 115, we said, because the standard deviation for IQ scores was 15 and the mean was 100, right? So we would know that 68% of the population would be expected to have an IQ score between 85 and 115. What about 2 standard deviations outside of the mean or beyond the mean? So let's take a look. It turns out that most people will be between 2 standard deviations of the mean, because that's 95%. 95% of the population will have their data values lying within 2 standard deviations of a mean for any normal distribution. So that would mean that if it was IQ scores again, if you went 2 standard deviations to the left, we'd be talking about 100 minus 15, that's 85, minus another 15, now we're down to 70. So an IQ score of 70 would be 2 standard deviations below the mean. An IQ score of not 115 but 130, that would be 2 standard deviations above the mean. So what we'd be saying here is that 95% of people would have their IQ scores between 70 and 130. So most humans would have their IQs between 70 and 130. Only 5% would not. Those would be in the tails. So 2.5 would be on the low side and 2.5 would be on the high side. Okay, there's one more standard deviation that we're going to need to memorize, and that is 3 standard deviations from the mean for the empirical rule. 99.7% of data should lie within 3 standard deviations of the mean anytime we have a normal distribution. That means, again, that if you were to go out 3 standard deviations for IQ scores, that would be a score of 145 on the right. And down here, at 70 minus 15, we're down at 55. So 99.7% of the population should have their IQ score between 55 and 145, because that's 3 standard deviations in both directions from the mean of 100. Okay. So if you wanted to break this into bite-sized pieces for yourself in your notes, and I think the notes that I provided for you online actually do this for you, but let's see where they come from. If 68% of all data lies within 1 standard deviation of the mean, and I did this in blue for you, what is 68 cut in half? Yeah, that's right, 34. So we'd have 34% in each piece here, because 34 plus 34 is 68. So there's that 68% we're talking about. 34% would be greater between the mean and 1 standard deviation above, and 34% would be between the mean and 1 standard deviation below. Or 68% is within 1 standard deviation of the mean. Now here's where things get a little interesting with our arithmetic. We said that 95% of the data values should lie within 2 standard deviations of our mean. So let's take a look at how this would play out. So that means from here, 2 standard deviations to the left, to here, 2 standard deviations to the right. Underneath that curve should be a total of 95%. But if we've already done 68% within 1 standard deviation, to get these 2 pieces, the total here, we would need to subtract what we've already talked about, the 95% minus the 68%. And when I do that, I get 27%. So that would mean that 27% would be the total of these 2 pieces, wouldn't it? Because this, and this have to add up to 95. Well, if I wanted to know exactly what each piece is, since it's symmetric, they should be the same, right? So if I divided 27 by 2 to cut it in half, we would get 13.5. So we get 13.5% in this region and 13.5% in this region. So if I wanted to know the percentage of people who would have IQ scores between 1 and 2 standard deviations of the mean, that would be between the IQ score, I believe, of 115 and 130. That's only 13.5% of the population, so not too frequent, right? One last piece of the puzzle to write down here. We were told that 99.7% of all data should lie within 3 standard deviations of the mean. So what does that mean for us in these two pieces? Well, we know that from this value, 3 standard deviations below the mean, and this value, 3 standard deviations above the mean, between these two values live 99.7% of the population, right? 99.7% live between here and here. So in these tails, that's a teeny tiny amount to split, right? So if I wanted to just know what's in these regions, I would have to subtract what I've already talked about. 99.7 minus the 95% that was within 2 standard deviations. And when I do that, I get 99.7, so I'm going to have 0.7, and then 4.7 it looks like. So 4.7 cut in half divided by 2, since it's symmetric, would give me these tails, not tails rather, but these pieces before the tails. That's 2.35% in each of those pieces, those regions. So only 2.35% of the population lies between 2 and 3 standard deviations below or above the mean. Now, if you wanted those itty-bitty tails, that would just be 100% minus 99.7 and then cut it in half, and you'd have those tiny, tiny, tiny pieces right there. So this is going to be helpful in answering our next question, where we know that we have, let's say, SAT math scores, which are normally distributed, and we want to know the percentage or the likelihood of someone having a certain SAT score above a cutoff value, below a cutoff value, or between 2 cutoff values. So let's take a peek. Okay, so here we have an example 2. It says SAT math scores have a mean of 500 and a standard deviation of 100. We're asked to find the percentage of students who have SAT scores, and the first one is between 400 and 600. So to get started here, we would need to notice that SAT math scores are in fact normally distributed. They would tell you that. So we would draw ourselves a bell curve. What's the next thing that we did? That's right, we would put our mean in the middle. So let me switch gears here so I can write a little clearer. So if we put our mean in the middle, there's my X bar, my sample mean. The mean was given to us as 500. So if the mean is given to us as 500, we can say 500 is in the middle here. And then we're told that we want to know between 400 and 600 for those math scores, those X values. Well, since the standard deviation, S for a sample standard deviation, was given to us as 100, I could go up 100 and I'd be at 600, or I could go left or down 100 and I'd be at 400. In other words, I'm talking about the region between 400 and 600. Now my picture is not perfect. It should be a lot prettier, a lot more symmetrical looking. Let me see if I can make this a little prettier. Something like that maybe. Not perfect. You could tell that your professor needs to work on her art skills. Okay. But these should be the same distance away because they're both 1 standard deviation to the left and to the right, it appears. And we would like to know what percentage of the population lives in here. Well, we know, according to the empirical rule, that 68% are within 1 standard deviation of the mean. And isn't that what we're dealing with here? So if we remember that 68% of the population are within 1 standard deviation of the mean, and that is what we have exactly within 1 standard deviation of the mean, the answer here should just be 68%. So the answer that we're looking for is just 68%. So that would be the likelihood that we would have of having an SAT math score between 400 and 600. Let's look at our next one. It says, what's the probability or percentage of scoring an SAT score above 700 for X? Well, once again, our mean for SAT math scores was given to us as 500. The average SAT math score in the nation is 500. The standard deviation was given to us as 100, so 1 standard deviation above the mean is 600. 2 standard deviations above the mean is 700. Let's go the other way. 1 standard deviation below would be 400, and 2 below would be 300. Notice I wanted to get the symmetry there, even though it didn't mention the 300. It only mentioned the 700. Well, since I have 2 standard deviations above, and then here at 300 would be 2 standard deviations below, between here would be what percentage? We know according to our empirical rule, you can check your notes, that within 2 standard deviations of the mean, lies what percentage? That's right, 95%. So if you remember that from your empirical rule, that 95% of data values lie within 2 standard deviations, you know that in this region is 95%. Now here they're only asking, what is the probability of being above 700? Well, let's think about what that means. What they're suggesting then is that we find the region to the right of 700 as our cutoff, right? This is what we are after. That's what we're after here. Well, we know that if you have 95% between 2 standard deviations and the total under the entire curve is what percentage? The entire curve would have a total of 100%, and we've already used up 95% between 2 standard deviations. What would be left for the tail regions? 100 minus 95, 5%. Good job. So for the tails here, the tails together, you'd take 100% minus 95%, which is 5%. Now that's the total in both tails, right? But we need to only look at the tail to the right because we only wanted above 700. So if you cut that into 2 to divide evenly, we would have 2.5%, wouldn't we? So that would be the amount in this region here and also in this region here, so that we add up, in fact, to 100%. So the answer to this question is just 2.5%. That's the likelihood of scoring an SAT math score above 700. So if your friends tell you, I got a 740 on my math SAT, maybe they're telling you the truth, but it's highly unlikely. All right, let's take a look at our last part of the example. What would be the likelihood of scoring below 300 on the SAT? To begin again, we would start off with our mean in the middle, and our mean in the middle was 500. Since 300 is below the mean, I'm going to take 1 standard deviation in each direction, right? So I'm going to say I could go down by 100, that's 400, and then another 100, there's my 300. Hey, this is the same setup as last time, isn't it? Above it would be 600, and then 700, 2 standard deviations. So just like last time, we can use the same trick. 95% of our data values are within 2 standard deviations of the mean. So that means that this is 95% between those 2 values of 300 and 700. But we're asking you to find, in this case, the percentage of the likelihood of scoring below 300. Well, that would be this tail, wouldn't it? So if we already did the math last time that each tail had 2.5%, then don't we have our answer? That's right, it would just be the same as getting above 700. So interestingly enough, I wanted to show you that symmetry. You were just as unlikely to have an IQ score below 300, not an IQ score, I'm sorry, an SAT math score below 300 as you were to have an SAT score above 700. They were equally as likely based on the symmetry. They were both in the same spot, the same tail, but just on opposite sides. And based on the symmetry, it's the same percentage. Okay, so in this video, we've talked about the basics of the normal distribution. The empirical rule was vital, memorizing that 95% of all data lie within 2 standard deviations. That's also known as the range rule of thumb, that part. But the other parts make up the empirical rule as well. 68% lie within 1 standard deviation of the mean, and 99.7% lie within 3 standard deviations of the mean. You'll need to know those facts and use those facts to be successful in this section. Also, we noticed that different types of distributions and how the ideal one was our normal distribution because of the high degree of symmetry and because we had our mean, median, and mode and mid-range all the same in the center of that graph. All right, so it's up to you now to practice because as we know, math is not a spectator sport. I'll see you next time.